Welcome to part 2, the unit circle. Suppose a circle of radius 1 unit is drawn on the coordinate plane, centered at the origin. The coordinates of the points where the x-axis and the y-axis intersect the circle can then be determined. So, if you take a look at the picture here, you can see that if the radius is 1, then where the circle intersects the coordinate plane has coordinates of 1, 0 here. If you go up to 90 degrees, okay, that would be 0, 1, because again, x would be 0 and the line is now vertical. If we keep going around the circle to 180, we're now in a quadrant where x is negative, okay? And then down to 270, we're in a quadrant where y is negative. Okay, so why is it called the unit circle? Well, it's because the radius is 1 unit. Is it possible to find coordinates of other points on the unit circle? Of course. So, if you were to take and draw a radius in quadrant 1 halfway between 0 and 90 on our picture. So we go right about here. Okay. What angle is produced between the x-axis and the radius? Well, halfway between 0 and 90 would be half of 90, so that would be a 45-degree angle. Okay. If a line is drawn straight down from the intersection point to produce a triangle, what type of triangle is this? So we put a line straight here. That makes that a right angle. And if that's 45 and that's 90, then what does our third angle measure? Well, 45 and 90 is 135. All triangles add up to 180, so 180 subtract 135 makes 45 degrees. So what kind of triangle has two angles the same? A right isosceles triangle, meaning that this side here and this side here are equivalent. Okay, so that brings us back to our special triangles from Math 20-1. We had 45, 45, 90 triangles and also 30, 60, 90 triangles. So, based on the information above, we know that a 45, 45, 90 triangle is a right isosceles. Okay, so if our radius is 1, and this guy's x and this guy's y, because x represents horizontal distances, whereas y represents vertical ones. Okay, but in this case, I know that x equals y. How can I figure out the length of side x? I can use, of course, because it's a right triangle, the Pythagorean theorem. So a squared plus b squared equals c squared. A is x, so x squared plus b is y squared, and c is 1 squared. Now, in this case, because it's isosceles, I know that x equals y, so in place of y, I'm going to put another x, so that I get x squared plus x squared. That gives me 2x squareds if I collect like terms, and now I can solve for x. Okay, so square root of 1 is 1, square root of 2 I can't do, so I have to leave it as a radical. I can, of course, rationalize that radical by multiplying the top and bottom by root 2. So x is plus minus root 2 over 2, but of course that's the same thing as y. Remember that the plus and minus comes from the fact that you are square rooting, and of course you get two answers when you square root a value. Okay, good. Now, 30, 60, 90 triangles, those of course come from equilateral triangles to start with. So equilateral has all sides the same, and all angles, interior angles, also equal, and they measure 60 degrees, because 180 divided by 3 is 60. Now, if you were to take a line and draw it straight down from the top, you would produce two right triangles of equal size, congruent, okay? And so you would get this situation. So this produces a right angle. This is still 60 degrees. This is half of 60, so 30. And now we have a 30, 60, 90. Now, if this is my radius from my unit circle, then that measures 1. This distance here is half of 1. So that's going to be a half. And how do we figure out y? Okay, again, we'll have to use Pythagorean theorem. So a squared plus b squared equals c squared. In this case, though, we're looking for b, so we want to go b squared equals c squared minus a squared. So that becomes 1 subtract 1/2 all squared. A half squared is a quarter, because that's a half times a half. So that's 1 minus a fourth, or 3/4. 1 whole is 4/4. So that's b squared. So to get b, I would square root both sides. So I can't square root 3, so it has to stay under the root sign. But I can square root 4, and the square root of 4 is 2. Okay, so in this case then, y would be root 3 over 2, x is a half, and the radius is still 1. Okay, on to the next page. Now, notice that the Pythagorean theorem was used to determine the missing side lengths. Put into the context of the unit circle and coordinate plane, the Pythagorean theorem can be written as r squared equals x squared plus y squared. R is the radius of the circle, x is the distance the point on the unit circle is from the y-axis, and y is the distance the point on the circle is from the x-axis. Okay, so I'm going to add a page here because we're going to making some, doing some conversions. We want to convert 30 degrees, 45 degrees, 60 degrees into form. So remember that pi over 180 is equal to x over, in this case we're going to go with 30 degrees. So when we cross multiply and simplify, we get x is equal to pi over 6. Pi times 30 divided by 180. 30 divided by 180 is 1/6, so we get pi over 6. Okay, pi over 180 is equal to x over 45. 45 times pi divided by 180 gives us pi over 4. And 60 degrees, that's pi over 180 equals x over 60. So that gives us x is equal to pi over 3. We did 90 degrees on a previous example. We know 90 degrees to be pi over 2. Okay, and so let's go back to our previous page and apply that information. Okay, so remember we start the unit circle at 0 degrees, which is also 0 radians. Okay, then this is 30 degrees, which we know is pi over 6. 45 degrees, or pi over 4. 60 degrees, and that's pi over 3. 90 degrees, and pi over 2. Okay, let's keep going around. Sorry about that. Let's keep going around the circle with our degrees. So this is 30, and another 30, and another 30, so another 30 makes 120. And then between 30 and 45 was 15, so that makes 135. And this would be 150, because we add on another 15. And we know that's 180. Keep going. 210, 225, 240, 270. A little ahead of myself there. 270, 300, 315, 330, and full circle puts us back at 360 degrees. Okay, we're going to keep going with radians as well. So let's go back to our other page, and we want to convert 120 into radians. So pi over 180 equals 120. So that gives us 120 times pi divided by 180. That gives us 2 pi over 3, because 120 is 2/3 of 180. Again, you can pause the video at any time to check out your calculator and check that these are okay. Okay, let's keep going. 135, so pi over 180 equals x over 135. 135 times pi divided by 180 simplifies to 3 pi over 4. Okay, and we also had 150, so let's convert that. So pi over 180 equals x over 150. And again, cross multiplying gives us 5 pi over 6. And of course, we know that 180 is the same thing as pi. Okay, so let's put our new radian measures on our unit circle. So 2 pi over 3, 3 pi over 4, and 5 pi over 6. Okay, so this guy would be 2 pi over 3, 3 pi over 4, 5 pi over 6, and straight out pi. Okay, you should be seeing some patterns starting to form. Okay, notice that 30 degrees is a pi over 6 and 150 is a pi over 6. So 30 degrees is 30 degrees above the x-axis. 150 is also 30 degrees above the x-axis. Okay, 45 degrees above the x-axis and 135 degrees above the x-axis. And notice that they're both pi over 4s. 60 degrees above the x-axis and the 120 above the x-axis. And guess what? They're both pi over 3s. So, can you predict the denominators for the rest of these? So, 210 is 30 degrees below the x-axis, so it should also be a pi over 6. Okay, and we'll figure out what the numerator is in a moment. Okay, whoops. All right, then 225 is a 45 degree below the x-axis, so that's going to have to be a pi over 4. 240 is a 60 degree, so that's going to be a pi over 3. 270 is opposite the 90, so that's going to be a pi over 2. Okay, this guy is a 60 degree, so that's going to be a pi over 3. This one's going to be a pi over 4. And this one is a 30 degree from the x-axis, so it's going to be a pi over 6. Okay, so now we can use our work with fractions to help us figure out, sorry again, keep hitting the wrong buttons. So then we can figure out what the numerators are. So this is 1 pi over 6, 2 pi over 6 is the same as pi over 3. 3 pi over 6 is the same as pi over 2. 4 pi over 6, 5 pi over 6, 6 pi over 6 is pi, so the next one must be 7 pi over 6, followed by 8 pi over 6, which reduces to 4 pi over 3, 9 pi over 6, which reduces to 3 pi over 2, 10 pi over 6, which reduces to 5 pi over 3, and 11 pi over 6 does not reduce. Okay, good. So we have all of those ones down. Let's go to the pi over 4. So 1 pi over 4, 2 pi over 4 is the same as pi over 2, 3 pi over 4, 4 pi over 4 is the same as pi, so then this one has to be 5 pi over 4, 5 pi over 4 and another pi over 4. In case you're wondering what I'm doing, I just keep adding pi over 4s, or the same as adding 45 degrees. So that would give me 6 pi over 4, but that reduces to 3 pi over 2, and I divide them by 2, so that's all good. And then add another pi over 4 to 6 pi over 4, so that would give me 7 pi over 4. And then another pi over 4 would give me 8 pi over 4, which of course gives me here 2 pi. 8 pi divided by 4. Okay, good. I think we now have everything on the circle labeled in terms of degrees and in terms of radians. Okay, so you can see that there are definitely some patterns going on here. Okay, so we can also connect them horizontally. And if you notice, the dots I connect have the same denominator for their radian measure. Okay, so for example, 210 is a pi over 6. We go across. 330 is also a pi over 6. Go up, pi over 6, pi over 6. They all have pi over 6s, okay? All right, so that's just another little pattern that you can use to help you remember what the angles are in terms of radians. Great. Let's move down to the next section. So, what do the coordinates look like for the other three quadrants? Well, we haven't figured out what the coordinates look like for the first ones because, of course, we've just been working on figuring out the angles in degrees and radians. So now we're going to use our information from the previous page in our special triangles to help us figure out what the coordinates are of the other points. I'm going to erase all of these stuff here that has to do with the degrees and radians so that I can fit the coordinates on. Now, please remember that when you're done, we can take a look. There is a completed unit circle provided in the reference section on the website. So when you're done this, I want you to go take that one out and you can use that, print it off and hang on to it because you're going to need it a whole lot while you're doing this whole entire trig unit. Okay, so I'll get rid of all of the angles and we'll start putting coordinates on. Okay, so if you remember from the previous page, this was 1, 0, and negative 1, 0, 0, 1, and 0, negative 1. Okay, so when we were looking at 45, 45, 90s, then that of course was this one right here. That's our 45-degree angle. So what were the coordinates of it? Well, remember that x and y were both the same. So if you look at the previous page, okay, x and y both equaled plus and minus root 2 over 2. Well, how do you determine whether they're positive or negative? Well, that's where the quadrant comes in. So if we were to write coordinates for this point, notice that we are positive x-axis and positive y-axis, which means that both my root 2 over 2's are going to be positive values. Okay? Good. So anything that had a 45 degrees or a pi over 4 is all have the exact same coordinates because they're all the same distance from the x-axis. All you have to worry about now is whether they're positive or negative. So in this quadrant, x is a negative, but y is a positive, so we're going to write that as negative root 2 over 2, comma, positive root 2 over 2. Okay? Let's go into quadrant 3. Here's my 45-degree angle there, or my pi over 4. So, again, it's going to be the same distance from the x-axis as it is in quadrant 1 and quadrant 2. So, it's still going to have the exact same coordinates, but now x is negative and y is negative because of quadrant 3, that's what they are. So that's negative root 2 over 2, comma, negative root 2 over 2. Good, and of course the fourth quadrant, x is back to being positive, y is still a negative, so this will be positive root 2 over 2, comma, negative root 2 over 2. So those will be the coordinates of all the 45s. Okay, now if we go back to the 30, 60, 90 triangle, the side that is opposite 30 will be a half, and the side that's opposite the 60 will be a root 3 over 2. And again, remember that these are going to be positive or negative depending on which quadrant they are in. Okay, so let's just keep that in mind. So opposite the 30 is going to be a half, and opposite of 60 is going to be root 3 over 2. Okay, so here I have my first 30-degree angle, okay? So opposite the 30 is a half, and opposite the 60, because if that's 30, then this guy up here has to be a 60 if this is 90, because they all add up to 180. So this is going to be the root 3 over 2. So that's my x value. So x would be root 3 over 2, and y would be 1/2. Okay? Now, if we go up to the 60-degree triangle, that guy is backwards to the one we just did, so my coordinates are going to switch places. This is 60, so this side would become my root 3 over 2, and this side becomes the half. So my x is now a half, and my y is root 3 over 2. Okay? Good. So again, coordinates will be the exact same, just positive or negative depending on what quadrant they're in. So if you think about this quadrant 1, and if you take it and just reflect it onto quadrant 2, that would be a horizontal reflection, so it takes all of your x values and makes them negative. So this becomes negative 1/2, comma, positive root 3 over 2. And this one becomes negative root 3 over 2, comma, positive root 3, or 1/2, sorry. Okay, good. Again, take your points and reflect them. But now this time it's going to be a vertical reflection, which means our y values also become negative. So if that guy gets reflected, that becomes negative 1/2, comma, negative root 3 over 2. Okay, and this one gets reflected down here, so that becomes negative root 3 over 2, comma, negative 1/2. Okay, and lastly, we're going to reflect them one more time. So again, I'm going to reflect them back here, so that's a horizontal reflection, which means my x changes signs to become a positive. So that's 1/2 positive, comma, negative root 3 over 2. And again, that works because we know that the x-axis in this side, in quadrant 4, is positive, whereas my y-axis is a negative. Good, and we flip over this point here, and we get positive root 3 over 2, comma, negative 1/2. Okay, these coordinates are also all on the unit circle in your reference section. So if I were you, I would draw another circle and practice doing this over and over again until you have them well remembered, because you're going to be using these from now on in this unit for trigonometry. Okay, so when we have angles in quadrant 1, they are known as reference angles. Okay, so the reference angles help us to figure out the coordinates for everybody else. So technically, really you just have to remember what the angles and the coordinates are in quadrant 1, and then just use that to reflect, as I did, into the other 3 quadrants to figure out the coordinates there. Okay, again, lots of practice with this will make you proficient at it and will definitely help you down the road. Okay, so practice, again, page 186, and don't forget to show your teacher when you're finished. Thanks a lot.